This is lesson 11, section 4.1 for MIT 175, and we're looking at polynomial functions and models. Okay, determine which of the following polynomials are functions. So, in order for it to be a function, the leading exponent has to be, the exponents have to be real, have to be non-negative, and they have to be not within a radical. So this first one we could say is a function with a degree of 8, and we look at the degree with the highest exponent for x is the degree. Okay, for b, this is not a polynomial because we have this would be an x in the denominator. So this was it could be considered a ratio of two polynomials in one. So it's not a polynomial. And so this one here, this is a polynomial. This would be considered x to the 0 plus 5. Well, anything to the 0 power is 1. So when there's no x there, it's a degree. It would be like x to the 0 plus 5. And so that would be a degree of 0. For D, if we FOILed x times x, we get x squared. So this would be a degree of 2. Now this one has a negative exponent for x, so it is not a polynomial. And then the last one, this would be a degree of 3. Because the x is non-negative and the leading exponent is 3. Now, a rule of thumb for polynomials is if you can put your pen or pencil on the paper and not leave the paper and not make any corners or cusp, then you have a polynomial function. So here's several reasons. This is not a polynomial. One is you get a corner. Another is you get this cusp where it comes up and then it comes back down. And then there's a gap here. That's another reason why it's not a polynomial, or a hole. Okay, so here we have the degree is, in this case, n. Whatever that leading exponent is, that's your degree. So this would be degree of 1, degree of 2, 3, and 4. Okay, now the higher the exponent, the more steep your parabola becomes, and more kind of like flattened out at the bottom it becomes. So this would be like n to the 4th, and so you still get that x is 1, y is 1, but then x is 2, and then it would be 2 to the 4th would be 16, so it would really make it steep. And then x to the 8th, that would be way, even higher than that. And then this is the properties of a positive integer even function. It will be respect to the y. It'll be symmetric. It'll be an even function is similar to x squared. An odd function is similar to x cubed. And let's see, the domain, that's going to be all real numbers because it's not within, it doesn't have x in the denominator, it doesn't have x in a radical. So all of these are going to be all real numbers for their domain. Okay, and you still have that negative 1, 1, 0, and positive 1, 1 for your even integers, your even functions. As the exponent increases, the magnitude increases, it becomes, more steeper. Alright, and here we have x cubed, x to the 7th, x to the 11th, you have these odd functions. So it's going to be similar to x cubed. Any of the odd exponents are going to be similar to x cubed. Where here's x cubed blown up, picture of it. Here's negative. This only goes from -2 to 2. So you're going to have, if this is 2, 4, 6, this is 4, 8, 12, 16, then this would be 2, 8 right here, because it's 2 cubed. And so the x to the 7th is also similar to x cubed, but now it becomes more steep. And then x to the 11th even more steep than that. And so this is just another illustration of that same thing. Okay, odd functions is symmetrical with respect to the origin, where you get 1, 1 on one side, -1, -1 on the other side, and 0, 0. Alright, here we have an x to the 5th. So that's going to be similar to x to the 3rd. And you have a negative in front of that, so that would be similar to -x to the 5th plus 1. And so that means this is going to reflect about the x-axis. It's going to be like x cubed. It's going to reflect about the x-axis, and it's going to shift up 1 because it's a positive 1. So this would be the same thing as if we were to say -x to the 5th plus 1. Okay, so there's your x to the 5th graph, and there's the reflecting about the x-axis. So it was up and to the right, down and to the left. Now it's up and to the left, down and to the right, and then it shifts up 1. Okay, and so here's that negative x, y equals x, -x to the 5th plus 1. Sometimes students like to see it written this way, so if you have trouble with it like this, then just switch them, keep the signs the same, but just switch the order, and you may find it a little bit easier to work through. Okay, now here we have f of x equals 1/2 x minus 1 to the 4th. Well, if we were to multiply this x minus 1 times x minus 1 times x minus 1 times x minus 1 4 times, you'll see this is x to the 4th, and then FOIL them, you see this is x to the 4th. So whatever exponent you have outside of the parentheses, that's what your degree is. That means this would be, if you FOILed it all out, you would get x to the 4th. Okay, so this is going to be similar to, is it going to be similar to x squared, or is it going to be similar to x cubed? Because it's even, you should have said it's going to be similar to x squared. And so it's going to be like a parabola, but it's going to be more flattened out. And we have this 1/2 here. So is that going to cause vertical stretching or compression? You should have said, because it's a fraction, you should have said that it's going to cause vertical compression. It's going to flatten it out. And then this is going to shift it which way? X minus 1 is going to shift it, you should have said, to the right. So here's our x to the 4th parent graph. And there's that 0, 0, and then x is 1, y is 1. X is -1, y is -1, just like with x squared. And now we're going to shift that vertex to the right. And that's still going to be to the right 1, up 1, to the left 1, up 1 from the vertex. No change, nothing different here so far from the parabola. And so now there it goes, you've vertically compressed it. So now this would be like over 1, up 1/2, and left 1, up 1/2. Or you could go 1, 2, and then up 1. It would be the same effect. Alright, and there's our transformations for our x to the 4th. Okay, we want to identify the real zeros. When we talk about real zeros, we mean the x-intercepts. Alright, so we want to find the x-intercepts. either it's going to touch, come up, touch, and then go back down, or it's going to go through the x-axis. Either way, these are going to be 0 for the y, but they're going to intercept or touch the x-axis. And notice this comes down and then through, so the y value is negative here, positive up here, and then it's going to positive here but negative before. It's going to be positive before the point, negative after the point. Whereas here it's going to be negative before the point, and then here's the point, and it's going to, the y values are going to be negative again. Here the y values are negative before the point, but positive after the y values are positive after the point. Okay. All right. If a function and r being a number, x minus a number is a real number for which f of r is equal to 0. In other words, if you were to substitute a number in and get 0r out, then r would be considered a real number. In other words, whatever you find for your real numbers, when you substitute that into your equation, you should get 0 out. Okay? R being a factor like x minus 2. The 2 would be r. So here, like, this is x minus r here. X minus r. The r is going to be, and then is going to be your 0. So r is the x-intercept. Okay, and so r is a solution of the equality. So whatever we put in for our 0, our x-intercept, into the equation, we should get 0 out. So that's a way to check to see if that your solutions are right. Okay, we're going to find a polynomial of degree 3 whose zeros are -4, -2, and 3. Okay, and so we use a graphing utility to verify it. Alright, so basically this would be A is going to cause that vertical stretching, right? But it really doesn't, for our zeros, that's not going to change it, so we can just leave that as A. So we're going to look at this as x minus r. Okay, that's this, x minus r here. So this would be considered like x minus r, but since the r is a -4, this would be like saying x minus a -4, and that makes it a +4. And then this would be x minus r2, well that's -2, so that's x minus a -2, so that makes it a plus. And then this is going to be x minus 3. Okay, so from there, we go ahead and FOIL that, and we get x, first you FOIL these two, and then you FOIL it with that one. And we get x cubed plus 3x squared minus 10x minus 24. So in other words, this would be x times x is x to the x squared. You got 2x and 4x. That's 6x, so that's x squared plus 6x plus 8. So you take that x squared plus 6x plus 8, and then you FOIL it with the x minus 3. And so you would do the x, distribute the x to the x squared, the x plus 8, or plus 6 rather, and then plus 8, and then it just distribute the 3. The -3 times x squared, -3 times 6x, and then -3 times the 8. And then you get this. Okay, and you notice the a is still in parentheses as outside of the parentheses. And so what the a does is the a, your intercepts are going to be the same. Your intercepts are here at -4, -2, and 3. Now the a would make this steeper. It would stretch it, stretch it, stretch it. But the intercepts would be the same. So a really doesn't matter what that number is. That's not going to change these intercepts here. It'll change like the steepness of the graph, but it's basically going to be the same. So we can assume that a is equal to, we can just say, alright, a equals 1. and then we just drop the a altogether. Alright, so why have a? Well, because sometimes there is a number there. Okay, and here the negative is up front, so it reflects. The intercepts are the same. It just, here this is going down and to the left, now it's going up. And this loops up in between -4 and -2. Now it loops down between -4 and -2. And then here between -2 and 3, it loops down, and here between -2 and 3, it loops up. And then 3 on, it goes up to the right. Here it goes down and to the right after 3. Okay, and so in this case, A would be 2. Well, how do you know what A is? Well, they would have to give that to you. And so here, see, here you're getting steeper. That this A, this part after -4 is steeper than before that. And see, between -2 and -4, you get this bigger loop here. And then you get a bigger loop down there and so on, between -2 and 3. Okay, so that you can see that does that. Okay, so you have this x minus r to the m power. So what that means is you can have this, these two would have to be the same. If x minus r to the m power is a factor of a polynomial, and you have x minus r, and then this would be this would be considered a different exponent than the original one. It's not a factor of f. There is, r is called a zero of multiplicity of m. So this would be, let's say r was 2, and let's say this m up here was a 3. So this is x. Let's say this is x minus 2 to the third power. Then this would be, the 0 would be a 2 with a multiplicity of 3. Okay, so here we would have a 0 of 2 and multiplicity of 1. This would be a 0 of -1 with a multiplicity of 3. And this 0 would be 3 with a multiplicity of 4. So in other words, this here, x minus 3 to the 4th, that would be like saying x minus 3 times x minus 3 times x minus 3 times x minus 3 times x minus 3. So that would be x minus 3 times itself 4 times, and so on. So the 2 is a 0 with a multiplicity of 1, because the exponent is just a 1. Alright, and the next one, we went through all that. Okay. Alright, find the X and Y-intercepts. Well, the nice thing about these problems is that they're already factored. So all you have to do is take the factors and set them equal to 0. So this factor here is x, so you just have to set the x equal to 0. And this would be like saying x minus 3 times x minus 3. Well, since it's the same thing twice, you just have to say, put x minus 3 equals 0, and you get x equals 3. So you get your zeros, or your x-intercepts, are 0 and 3. 0, 0, and 3, 0. Alright, and so here we set y equals 0, solve for x. Well, it's already factored. So we just set our factors, x equals 0 to 0, and you just take that x minus 3, bring it down, x minus 3 equals 0, add the 3, and we get x equals 3. The y-intercept, that's easy. You just put 0 in for x. Well, this is going to be 0 times all of this. 0 times anything is still going to give you 0. So anytime you have an x-intercept that's 0, you're going to have a y-intercept that's 0. Okay, so that's kind of an easy thing to remember. Okay, turning points. If f is a polynomial function with degree n, then f has at most 1 less. So in other words, if your polynomial was a degree, let's say x cubed, then it would have at most 3 minus 2. It would only have 2 turning points in it. at most 2. So it would always be 1 less than what the degree is, the number of turning points. If the graph of a, so this in this case this would be 1 turning point, because it's going from increasing to decreasing, so that would be considered a turning point. And here this is going from decreasing to increasing. That's another turning point. So it's like, another way to look at it is opening down is 1 turning point, opening up is another turning point. So the turning point would be right at where the maximum, relative maximum, or the relative minimum is at. The graph of polynomial function has n minus 1 turning points. The degree of f is at least n. Okay, so that's going backwards. Now, if you have that many, in other words, if you have 2 turning points, then you know it's going to be at least an x cubed, could be an x to the 5th, and so on. But it's going to be at least an x cubed with 2 turning points. Alright, so we've done minimums with the graphing calculator before, so we're not going to really go into that too much. Okay, with which of the graphs in 16 polynomial is a function that could list the zeros and state the degree? Okay, so we could say that this first one here, it cannot be a polynomial function because of the gap in it. Alright. Now this one, we can say that is a polynomial function. And then what would the zeros be? Well, you should have said the zeros is -2, 1, and +2. Okay, and here they are down here. Alright, now would this be considered a polynomial function? And you should have said no, because it has that cusp and it comes down and then kind of doubles back. Alright, so that's not a function. And then this one here, would this be considered a function? And you should have said yes, because it's smooth, there's no corners, there's no gaps, there's no holes, there's no cusps, there's no corners. And so the zeros here would be what? You should have said -2 and 1. Alright, so the turning points. It's got 1 turning point, 2 turning points, 3 turning points. So the degree would be at least, you would add one more to that, 4. Okay, and you see how this opens down to the left. And so this would be similar to, this would be at least an x to the 4th. But it's going to be a negative, right? Because it's opening down, kind of like with a parabola that opens down, but it has extra turns in it. It's kind of like a parabola, but it has extra turns in it. Okay, for large values of x, either positive or negative. For a large absolute value of the graph of a polynomial. Okay, here we have a polynomial here. And so this would be similar to saying something like 5x to the 7th plus 3x to the 6th plus 5x to the 4th, and so on down to like 3. And so the power is always the highest exponent. It's always the leading exponent. Okay, so this would be similar to x squared or x cubed. Okay, this would be similar to x squared, right? Because it opens up and to the left and up and to the right, and it's got to be a positive leading coefficient, and it's got 1 turn, 2 turns, 3 turns, so it's going to be at least an x to the 4th, maybe more. Could be x to the 6th, x to the 8th. It has to be even because it's like x squared, but it's going to be at least leading coefficient of x to the fourth because of the 3 turns in it. And this way, it opens down. Still has 3 turns in it, but it's going to be like a negative, at least an x to the fourth, but with a negative leading coefficient. And this is just showing that it goes to y is going to negative infinity, and x is going to negative infinity, and so on. Alright, now this one here, this would be similar to x cubed, right? Because it's going up and to the right, down to the left, and it's got 1 turning point, 2 turning points. So it's going to be at minimum and a leading coefficient of x to the third. Could be x to the fifth, could be x to the seventh, but you know what? It's at least x to the third. Now this one here, this has got 1 turning point, 2 turning points, 3 turning points, 4 turning points. So this one's going to be at least an x to the fifth, and because it has 4 turning points in it. And it's an odd function, and it's going down and to the right, up and to the left, so it has to be a negative leading exponent. Alright, which of the graphs in figure 18 could be the graph of x to the fourth? And it's positive. And another thing you can notice is that when you put 0 in here for x to get the y-intercept, 0, 0, 0, 0, what's left? Negative 6. So it has to have a y-intercept of negative 6. So that immediately eliminates a, because that's a positive 6 y-intercept. Okay, now we've got a positive coefficient, so that means it has to open which way? Up. So that eliminates d, because that's opening down. So now we're down to these two. And so we've got an x to the fourth, so that's going to be 1, 2, 3 turning points in it. But this has got 1, 2, 3, 4, 5 turning points. So that means this one would have to be at least an x to the sixth. So that eliminates c. And so it would have to be b. Okay? And so we eliminated that one last, but it's the same process, basically. Okay. And there's our summary for our polynomials. It must be smooth and continuous. Pen cannot leave the paper. Cannot put corners or cusp in it. And have maximum turning points. Subtract 1 to give you a degree. Maximum turning points of n minus 1 for a degree. So if you had an x to the fourth, you'd have to have at least 3 turning points. That's what that means. At a 0 of even multiplicity, at a 0 of even multiplicity, the graph of f touches the x-axis. So if you have a function with a 0, with an even multiplicity, then it's going to touch. It's not going to go through the graph. Like if you had x minus 1 parentheses squared, that's going to touch the graph. It's not going to go through it. If it has an odd multiplicity, like parentheses x plus 3 close parentheses cubed, that one's going to go through the graph. Between zeros, the graph of f is either above or below the x-axis. The end behavior is going to, you're looking at basically either x squared or x cubed. Depending, and your end behavior is going to, you look at the leading term for that. Alright, so here we could say that 2x plus 1, it's got an odd multiplicity, so that one's going to go through that point. If you set a 2x plus 1 equal to 0, you get x equals negative 1/2. The line is going to go through negative 1/2. But here you set x minus 3 equal to 0, and you get x equals 3, so you have a 0 at 3. But because that has an even multiplicity, it's going to touch it and then go back in the same direction. Alright, and the end behavior, you look at the multiplicities. So you got a square here plus 1, so that'll make it a x to the third. So the end behavior is going to be like x to the third, because this would be like x times x is x squared, and x squared times x. By the time you FOIL it and distribute, you're going to get an x to the third. So you take your multiplicities and you add them together, and that gives you your end behavior. And since it's positive, it's going to open, it's going to be like x cubed up to the right, down and to the left. Okay, so here's our polynomial, and here we FOIL the x minus 3, and then you take the 2x, distribute that into each of the 3 terms, and then take the 1, distribute that into each of the 3 terms. And we get this. And there it is, 2x cubed. Like I said, you took the square, the multiplicities, add them together, and you get the end behavior. You look at the leading term for that end behavior. So this is going to be similar to x cubed. Alright, and so we have to combine like terms here. So you got negative 12x, positive 1x, will give you negative 11x, 18 and 6, and that'll be plus 24, plus 9. Oh, that's positive 18, negative 6. So you're going to positive 18, negative 6, and you're going to get a plus 12, x plus 9. So this will be at most 2 turning points. It's going to have an end behavior of x cubed. It's going to be up and to the right, down and to the left. We know it's going to go through one point and touch at another point. Okay, so we have a degree of 3. So it's going to behave like a 2x cubed. Okay, find the x and the y-intercepts. So basically we just take what's in the parentheses, set them equal to 0. And so we're going to get negative 1/2 and positive 3. Now for the y-intercept, you put 0 in here for x, 0 in here. So this will be 1 times negative 3 squared. Well, negative 3 squared is 9. 9 times 1 is 9. Well, it would be, if you can see it in general form, wherever you have the x's, that'll be 0, 0, 0. You just got to look at it and see that your y-intercept is going to be 0, 9. So it's a little bit easier to see it in when it's out in general form. Okay, to find the x-intercepts, you set the y equal to 0. Well, it's already factored, so that's a good thing. And so you just set each factor equal to 0. And so you don't have to worry about the multiplicity, because this is x minus 3 times x minus 3, so you just got to solve for 3, x minus 3 one time. Okay, and you get x is negative 1/2 and negative 1/2, 0. That's one x-intercept. The other one is 3, 0. Alright, and we said that the 1/2, that's an odd multiplicity, so it's going to go through the negative 1/2. And since it's up and to the right and down and to the left, that means it's going to touch the 3, come up, and then go through the negative 1/2. So we determine the multiplicity for 1/2 is 1, so it's going to cross that, and the 3 is the multiplicity of 2, so it's going to touch. Maximum number of turning points, we said that there was an x, this is going to be an x cubed, so a maximum of 2 turning points. Okay, a polynomial degree 3 with at most 2 turning points, because that would be the 3 minus 2 for the number of turning points. At most 2 turning points, the parabola that opens up. Alright, so this is what we've got so far. We know it comes up and to the right because it operates like a positive x cubed. It comes up and to the right, down and to the left. We know our zeros are at 3 and negative 1/2, and we know that our y-intercept is at 9. So we know that it comes down, touches, because that's a multiplicity of an even number, so it's going to come down, touch, come back up, go through the y-intercept and then go through the negative 1/2, because we know that's a multiplicity of an odd number. Alright, and so that's our graph. Now they get the negative, the 4/9 in there and 1/12. You know, here you can use the calculator to get the relative maximum for that. Okay, determine the end behavior. First you want to determine the end behavior by looking at the multiplicities, find the X and Y-intercepts. Again, you'll have to find them algebraically. Determine the zeros of the function. Where do they intercept the x-axis? By looking at the factors. Determine the maximum number of turning points. Take the highest exponent, subtract 1 from it. That's the maximum number of turning points. Determine the behavior of the graph of the x-intercept by looking at the multiplicity of each factor. Okay, and then draw your function. Alright, so we want to, first thing, end behavior. We have an x squared, we have an x, another x. So this would be like saying x squared, here's a multiplicity of 1, multiplicity of 1, so this would be 2 plus 1 plus 1, that's x to the 4th. So this is going to behave like a positive x to the 4th. Well, x to the 4th is even, and it's similar to a parabola, x squared. So it's going to open up and to the right, up and to the left. And, alright, so, excuse me, the y-intercept, you put 0 in here for x. Well, 0 times anything, right, is going to be 0, so right away, when you see a 0 out here, outside the parentheses, then you know that it's going to be 0, 0. Okay, so our y-intercept is going to be 0. 0, 0, 0. So that'd be like 0 times negative 4 times 1. Well, 0 times negative 4 times 1 is 0. And now for the x-intercepts, we set each factor equal to 0. So that'd be x squared equals 0, x minus 4 equals 0, x plus 1 equals 0. Well, the square root of 0 is just 0. Right? There's no plus or minus 0, it's just 0. And then this would be x plus 4 and x minus 1. Well, at 0, it has a multiplicity of 2. So that means, is that going to touch 0 or is it going to cross at 0? And you should have said it's going to touch. Now, the x minus 4 has an odd multiplicity, right? Multiplicity of 1. So it's going to go through the x-axis at 4. And it's also going to go through the x-axis at negative 1. Alright. So, let's see what we've got here. The graph, because it's an x to the 4th, will have at most 3 turning points in it. At most. May not necessarily be 3, but it will have at most 3. And there's our intercepts. Alright, so here we have our end behavior. It's an x to the 4th, so it's going to be up and to the right, up and to the left. It's going to, we said it's going to go through negative 1. I mean, it's going to go through it at x at 4. And our y-intercept is at 0, so we said it was going to touch at 0, come back down, and then go through at negative 1. The only thing that we don't know is how far down does it go and how far up does it come up in between 0 and 4. How far down does it go here and how far does it go down here? That's the only thing that we don't know. So at those you can just look at your get your relative minimum points there. And don't worry about this 5 to 150. I mean, as long as it's showing up and then up and to the right and up and to the left, you know, that's good. Okay, analyze the graph of the polynomial function. Okay, so we have a leading exponent of x cubed, so we know it's going to be up and to the right, down and to the left. And it's going to have at most 2 turning points in it. Okay, so we know that's going to be like an x cubed. And so this one here, because it's working with decimals, we go ahead and plug that into the calculator, and this is what it looks like. Okay, and then we use that calculator to find our intercepts because we're working with decimals. Alright. So here, because it looks like here's -5, here's -4, here's -3. So we know by looking at the calculator that after -3, it's -3 is going to have a positive y value, but -4 is going to have a negative y value, and that's what this is showing here. -4 has a negative, -2. They don't even show -3, but -2 has a positive y value. That's what this is. Here's -2. Here's -4. -2 is a positive y value. -4 has a negative. So you know it has to go through the x-axis because one y value is positive and the other y value is negative. Okay. And approximate the turning points of the graph. You know, we're just using the calculator for that. Alright. And so that's our function. Alright, here we have a table where we're working with cubic functions. And so you can see how it comes up and then down. So you know that you're going to use the cubic regression. And on your calculator, that's going to be, you're going to use stat calc 6 for cubic regression. And so you put your table of values in like you did before, and then you get your cubic, you put it in list 1 and list 2, and so you would go to stat calc 6 for cubic regression, and then L1 comma L2, hit enter, and you get your function. Okay, and so we're going to round these off to 4 decimal places. Alright, so we're not going to do the vars, just put it in like that. Okay, main thing is you're going to look at to see what your window is going to look like. Alright, and so we get our cubic function. Use the function found in part B to predict the cost of printing 22,000 texts per week. So we're going to put 22 in for X, and we get 176.8 or 176,800.